All right, hello everybody, and welcome to another exciting day in the world of dynamics. Today we're going to continue on with our coordinate systems. We've been covering rectangular coordinate systems up till now. Now we're going to start talking about normal and tangential coordinates. These are also known as path coordinates, and the reason they're called path coordinates is because the coordinate system travels along with your particle. So path coordinates. And within this path coordinates, if I think about a particle that's traveling with some kind of motion, and a lot of the times these will be circular motion, but whatever it might be, if I were to look at some point along this path, we're going to define our coordinate system as moving along with the particle, and we have two components to these path coordinates. Our first one being the tangential. So a unit vector is, we're going to designate as u sub t for tangential, and the other one being u sub n for normal. So we'll have a normal component and a tangential component, and as I move throughout this path, like if I move over to a little bit further down, I can see that my tangential would be following in that direction, and normal would point towards the center of the curve. I picked a place, it just happens to be somewhere in between, but we'll say it's something like this. They will be 90 degrees to each other, so that's supposed to be a little n there. You can envision how it would keep going. So to define these, our u sub t will be our unit vector. We talked about unit vectors before, having a magnitude of 1 pointing in the direction of the coordinate axis. So this is a unit vector in our tangential direction. And I want to say that our tangential direction has to be along the path, so whichever direction we're going. And that's why it is constantly changing, because as long as our path is changing, our tangential direction is changing. 90 degrees to that, we have our u sub n, which is the unit vector in the normal direction. And that's going to be towards the curvature. So usually towards the center of the circle, if it's a circle, or towards, I'll just say towards the curvature. 90 degrees away from the direction we're traveling with the path. So with these coordinates, we can now look at what acceleration and velocity mean. So let's say I'll say this coordinate system, maybe that's better. So with this coordinate system, sorry my handwriting is getting kind of messy. I'm kind of limited on time with this YouTube stuff, so I'm trying to write a little faster than I normally would. I can say that my velocity vector is going to be equal to my velocity times the unit vector in the tangential direction, because it is always along the path. And basically what that's saying is that I have a speed. My speed will always be going in this along the path in this tangential direction. I also know that my acceleration by definition must be equal to the derivative of my velocity vector with respect to time. So we've talked about that quite a bit. Well, when we talk about a vector, in this case velocity, there's two different components to a vector, or two different pieces to a component. One is the magnitude and one is the direction. So we're going to rewrite this acceleration vector as the v dot, and if you forgot what that is, that's basically my change in velocity with respect to time in the tangential direction. It's really your change in speed plus however fast we're going, our speed squared, divided by this rho value, which is our radius of the curve that we're traveling on, and then our normal, that's in our normal direction. So to define these things, my rho is going to be the radius of the curve of whatever I'm traveling on at that particular moment. And my a sub t, we're going to define as my v dot, which we've already defined as my change in speed. So this is change in speed. And that's what we're really familiar with. We always talk about acceleration as being the change in speed. But if you're going around a turn of course you're accelerating as well because you have a change in direction. So that is a change in our normal direction. So acceleration in the normal direction would be equal to this v squared over rho. So of course this is our change in direction. And if I have a change in speed and a change in direction, then I can have an overall acceleration. So if we ever talk about a total magnitude of acceleration, it won't have any subscript. From Pythagorean, we know that that's equal to our tangential squared and our normal acceleration squared. Square rooted, of course. And we have to talk a little bit about this path, because there is one other equation we have to talk about if I know y is a function of x. So let's say that when we have a known path, and this known path is y as a function of x, then I have an equation for this radius of curvature, which we'll need at least on one of our homeworks. It says that we have 1 plus, this is on the numerator, oh, can't write today, rho is equal to 1 plus the derivative of y with respect to x, that whole quantity squared, this whole numerator value to the 3/2 power, divided by the absolute value of the second derivative of y with respect to x. So that's another equation for just the radius of curvature, and that one is derived in the Hibbler textbook, so I'm not going to go through the derivation, or actually I don't even think it is in the book. I think it says go to your calc book to find it, so good luck. It's pretty much a plug and chug type thing. If you have y as a function of x, you can figure that out. Let's look at one example on how we use these path coordinates, normal and tangential coordinates. And for this example, we are going to be given some kind of race car. I'm just going to say it's a car, and this car is going to start from rest. Probably just say our initial velocity is equal to 0 on a circular racetrack. So this car is going around a circle, Indy 500 style. And it has a radius that's equal to 300 feet. So we're in standard units. We're going to be given that its speed increases at 7 feet per second squared. At 7 feet per second squared. And what we want to know, what we would like to find, is how long, or how many seconds, I'll just say how long, until my acceleration is equal to 8 feet per second squared. So you might even look at this problem in the very beginning and say, well, you're already giving me acceleration. Acceleration is equal to 7 feet per second squared, but then you're saying how long until the acceleration is 8 feet per second squared, so it looks like it would never be that way, because we're starting at 7, how would it ever go up to 8? Well, this goes back to the fact that there are two components to our acceleration. Our speed increasing at 7 feet per second squared is our tangential acceleration. So that's my v dot, right? That's my tangential acceleration is equal to 7 feet per second squared. Well, I also have this other component, which is my normal acceleration, my change in direction. Now my change in direction is going to require this little v. So from my v dot, I can figure out what my velocity as a function of time is, because I can just integrate this 7 feet per second squared to give me 7t. The reason I did that is because when I look at my normal acceleration, my a sub n, I know that's equal to v squared over rho, my v being 7t, so 7t squared, over the radius of curvature. It says it's a 300 foot radius to this racetrack. And I didn't draw a picture due to lack of time, but I think we can all get an idea. It's a circle, right? It's not too hard. This is like a bird's eye view, my little race car zooming on around, and at any point in time I have my acceleration tangential and my acceleration normal, something like that. where am I? So plugging that in, my basic equation would be my total acceleration is equal to the square root of my normal squared plus my tangential squared. Well, we know now that my normal is this 7t squared. If I square that, so I don't have 2 minutes, I'm going to simplify it in. I have 49t squared over 300, and then I'm going to square that. That's my normal plus my tangential, which is given as 7 squared, and I'm going to set the whole thing equal to 8 because I want to know when this total acceleration is equal to 8 feet per second squared. From that, just doing some math. Geez, I don't know how to simplify it too much. Looks like I'm just going to follow my notes. I have 2401 t to the 4th over 90,000 is equal to 64 minus 49. And solving for t, I end up with t equals 4.87 seconds. So that's similar to how a number of these problems are going to work. You're always looking at the normal and tangential direction, keeping in mind your speed and how acceleration has 2 components to it. So good luck, have fun out there, and we'll see you next time. Thanks.